Hi everyone. In this lecture, we'll try to understand the nonlinear behavior of a differential amplifier to sinusoidal inputs. Mainly, we'll look at what are the harmonics which will be present in a differential amplifier. In two cases, the first case here shown on the left, it's a constant voltage biasing. The second case here, it's a differential amplifier with a constant current biasing. In both these methods of biasing, we will try and analyze what are the harmonics that are present in the circuit, and we'll also see what kind of harmonics that is present on the supply or the ground lines. In fact, in this lecture, I'll generalize this, and what I've shown in the figure is a MOS amplifier circuit, but I'll generalize this to any three-terminal amplifying device. Now this can be a BJT, MOSFET or a vacuum tube device. So shown here is a generic three-terminal amplifying device configured in a differential amplifier mode. So this is voltage biased differential amplifier mode, and this is current biased differential amplifier mode. Now these are the single-ended counterparts for these differential amplifiers. So this is a voltage biased single-ended amplifier, and again this is a current biased single-ended amplifier. So this three-terminal generic device, I'm going to assume that if I apply a voltage V between the input terminals as shown here, then the current at the other terminal I is given by a nonlinear function where I is f of V. Now as I've shown here, the three-terminal device can be a bipolar junction transistor, a MOSFET or a vacuum tube amplifier. Now in case of a bipolar junction transistor, f of V, the nonlinear function will have an exponential dependence on the input voltage, and in case of a MOSFET, it will be a square law characteristic. So I've assumed beta here is some constant, it will be just a square law characteristic, and in case of a vacuum tube amplifier, it will be to the power 3/2. Now again, one should understand that these are all this is a zeroth order MOS model, and a more accurate MOS model will contain a more complicated dependence on the input voltage V. But I'm going to assume a generic equation like this, f of V, and try to intuitively understand what are the harmonic content that's present in the device, and also the harmonic content that's present in the supply line. Now let's start with a constant voltage amplifier, a constant voltage biased differential amplifier. What we are essentially going to do is that we are going to apply a sinusoidal input here, Vi, and then we are going a Vi of frequency omega naught, and then we are going to study the frequency content present in I1, I2, and then the frequency current content which is present in the supply voltage, which is nothing but the sum of the two currents. And finally, we are also going to understand what is the frequency content present in the differential current I1 minus I2. Because it's a differential amplifier, we are mainly interested in this component, in this term which is I1 minus I2. So that's what we are going to study in this lecture for both voltage biased and current biased differential amplifiers. So first I'll start with a voltage biased differential pair. I have shown here a MOS amplifier and then a generic amplifier here, a generic differential amplifier built using a generic three-terminal amplifying device. Now I'm going to assume that there is a common mode voltage VCM and a differential signal is applied on either of the inputs, on both the inputs. So on the one side you have plus Vi by 2, on the other side you have minus Vi by 2. So the current I1 flowing in this device is simply given by f of the voltage across this device here. V here is simply the gate voltage minus the source voltage, the voltage at this point minus the voltage at this point. So which is what I've written here, Vi by 2 plus VCM minus Vs, and I2 is minus Vi by 2 plus VCM minus Vs. And I'm going to call this VCM minus Vs as the bias voltage as Vx. Then I can express I1 and I2 as f of Vx plus Vi by 2 and f of Vx minus Vi by 2. Now one thing we need to understand is that f of x is a nonlinear characteristic. Now your I1, if I assume Vi is 0, if I apply a 0 input, then I1 will be equal to f of Vx will be equal to I2. So that current, I'm going to assume the nominal current as I0 by 2. So nominally, both the devices are carrying I0 by 2 and I0 by 2. Now on top of that, we are applying this differential input. Now, if I start from Vx, so Vx is the nominal bias voltage, and move Vi by 2 units on this side. This is the IV characteristics of this nonlinear device. If I move Vi by 2 units on this side, then the change in the current, I'm going to call it as delta I1. So this is Vx plus Vi by 2. This voltage here is Vx plus Vi by 2. Similarly, I'm going to move Vi by 2 on this side, on the other side of Vx, and I'm going to call the change in current as delta I2. Now, because it's a nonlinear characteristic, delta I1 will not be equal to delta I2. So meaning, if I apply a positive voltage Vi by 2, the current in the device I1 is increasing. It's increasing by a factor delta I1. And similarly, the current in I2 is decreasing because the voltage here at the gate terminal or the control terminal is negative. So therefore, the current is decreasing by delta I by 2. So I can write it as I0 by 2 plus delta I1 and I0 by 2 minus delta I2. Because it's decreasing, the other current I1 is increasing and I2 here is decreasing. But what we can see from this is that the nonlinear characteristics implies that delta I1 cannot be equal to delta I2 because it's a nonlinear characteristic. Had it been a linear characteristic, then if I move Vi by 2 on either directions, then the change in the current will also be the same. Now I'm going to make the analysis more clear, I'm going to assume that f of V has some kind of a nonlinearity which can be expressed as a series expansion in this way. So it has all the terms, all the powers of V, and I'm going to group the terms and I'm going to express this function f of V as an even function and an odd function. So I'm going to group all the terms which are odd powers of Vi and call it as f0 of V, fo of V, and all the even powers I'm going to call it as fe of V. So this is the odd part and this is the even part. So if I try to write an expression for I1 in a generic way, it's going to be I0 by 2. So that's this can be very trivially derived by doing a Taylor series expansion. So but I'm more interested in trying to intuitively tell you what's happening in the circuit. So I1 will simply be I0 by 2, which is the constant current flowing, plus the series expansion terms. So K1 Vi by 2 the whole Vi by 2 plus K2 Vi by 2 the whole square and so on. I can actually write it in a more simpler way as I0 by 2 plus f0 of Vi by 2 plus fe of Vi by 2. So even terms and odd terms. So I1 contains both even and odd terms. Similarly, I2, I can then expand it because now we have applied a negative input Vi here. All the odd terms will have a negative sign. Now the even terms, you are going to raise the voltage or a negative voltage to an even power. So that will be positive. So even terms will have same polarity here as it was in I1. So when you write the terms, you can write it as I0 minus f0 of Vi by 2 because they will all have the negative signs as compared to I1. And the even terms will have same polarity. So it will be fe of Vi by 2. So now the differential current is the difference between the two currents. So that is only going to contain odd harmonics. So all the even harmonics, because they have same polarity, they will get cancelled out. And the common mode current, or the sum of the two currents, I1 plus I2, will contain purely even harmonics. Again, this is something that is a well-known fact in differential amplifiers. If you look at the differential current, it will only contain odd order nonlinearities. And the common mode current, it will contain even harmonics. Now we can actually understand how is this even and odd harmonics flowing in the circuit. What is the way in which the harmonics flow, the currents flow in this voltage biased differential amplifier. So we have split it as two parts. So now if you see, I1 is simply I0 by 2 plus the odd part plus an even part, which is what we have shown here, and I2 again has an odd part and an even part. Now the interesting thing to observe here is that the odd part in I1 is exactly same as the even part, the odd part in I2 with a negative sign. The only difference is negative sign here. So that current, if I try to plot it, if I try to see the direction in which the currents are going to flow in a differential amplifier, so that's what I've shown it in this circuit here. So I've split the currents as odd current and even current. Now the odd harmonic currents, because any increment in I1, the odd harmonic increment is exactly equal to the decrease in the current I2, because if you see F naught of Vi by 2 is the increase in I1, then the decrease in I2 is minus of F naught of Vi by 2. So what will happen is that the odd harmonic current will flow in a loop like this. So you have an odd harmonic current coming this way and it will then flow into this device. So they form a loop like this. That's what is shown in this figure. The even harmonic current on the other hand, because both the currents are of same polarity, so these MOSFETs, both these MOSFETs are carrying the current with the same polarity, they both will flow into the source or into the voltage source Vs, or rather into the ground. Similarly, I can show that from the top, from VDD, the entire current that's going to flow through VDD, of course there is a DC current I0 plus all the even harmonic components. So I1 plus I2 comprises of all the even harmonic components. They will be flowing through this voltage source. So the current will come through voltage source, half of it will flow in this direction, the other half will flow into the other MOSFET, and then both these currents will again combine at the source end and flow into the ground. So this is the path or the trajectory of shown on a schematic diagram for the odd harmonic currents and the even harmonic currents. So that's what I've written here. So if I apply an input of certain frequency omega naught, then the individual currents I1 and I2 will contain the same all the harmonics of omega naught, which is determined by the nonlinear characteristics of the device. And the sum of the two currents, which is the current which is going to flow through the supply, will contain only even harmonics. And the difference between the two currents I1 minus I2, the differential part, will only contain the odd harmonics. Now again, this is something that's well known in differential amplifiers. I'm carrying out this analysis so that we can then, and it's easier to understand a differential amplifier with current biasing. Now in the presence of mismatch, both the devices are not going to have same characteristics. So there will be slight difference. I'm going to call the one device as F1, F, and the other device as F1 of V. So the characteristic is going to be slightly different between the two differential pairs. In that case, what will happen is that I'll just give the final intuitive result. Previously, when I added or subtracted the two currents, either the odd part or the even part was getting fully cancelled out. But now, if I am going to add the two, because the odd parts, because they will not get fully cancelled out, because there is a mismatch between the two devices, they will not get fully cancelled out. So therefore, some residue odd harmonic will still be present in I1 plus I2, which is the current drawn from the supply. And even harmonics are anyways already present. Okay, so the additional term that's present here is the odd harmonic terms. And similarly, in the differential current I1 minus I2, previously all the even harmonic current components were getting cancelled out, but now there will be some residual even harmonic current as well, in addition to the odd harmonic currents. So I have now pictorially shown the direction of flow of the odd and even harmonic currents in a differential amplifier with mismatch. Now if there is mismatch, we just saw that the sum of the two currents I1 plus I2 carries some additional odd harmonic current as well. That happens because an increase in this current. So for example, when I apply an input voltage, the current through this device increases and the current through this device decreases. But then as far as the odd harmonics are concerned, the increase in this device does not match with the decrease in this device. So there will be some residual error. And that current is going to come from the supply. So now if you see, There is an odd harmonic component which is looping around in the circuit in this way, which is seen by the pure differential circuit. There is also an odd harmonic component which is going to flow from the supply because of the presence of mismatch, and which, if a current flows from the supply, then it also has to flow into the ground. Okay, so, and in case of even harmonics, anyways, to begin with, all the even harmonic current has to fully flow through the supply, and it gets divided unequally here, because in this case both the devices don't carry same even harmonic component currents, because the characteristics are there is a mismatch between the two devices. But still the total current is going to come from the supply voltage. So this even harmonic current is in addition to the DC current I0, which is being drawn out of the supply VDD. So this is what happens in a voltage biased amplifier. So in case of mismatch, the differential current and the common mode current, or rather the current drawn from the supply, both will contain all the harmonics. Of course, the harmonics values are going to be lower. So for example, in a differential current, the even harmonic terms are definitely going to be much lower. Similarly, in case of the current drawn from the supply, the common mode current, the odd harmonic currents values are going to be smaller, and that's determined by the mismatch between the input pairs. Now just to quickly compare it with a single-ended amplifier. In a single-ended amplifier, the current drawn from the supply is same as the current drawn by this amplifier here, amplifying device. So if this amplifier has a nonlinear characteristic f of v containing all harmonics, then the current through this device will also contain all the harmonics, and the current through the supply will, which is nothing but the current through the device, will also contain all the harmonics. Now that's the fundamental difference between single-ended and differential. If there is pure matching, perfect matching between two pairs and between the two devices in a differential pair, then the supply will have to only supply the even harmonic currents. There will be no odd harmonics present in the supply. And if I take the output differentially, or rather take the differential current in a differential amplifier, you will have only odd harmonics. And the interesting fact here is that in a voltage biased amplifier, all the harmonics present in I1, I2 or in the entire circuit is completely determined by f of v. Okay, so now for example, if I assume f of v to be an odd number, again f of v, I have just written the nonlinear equations again for the three commonly used amplifying devices, the vacuum tube, MOS and BJT. I mean, vacuum tube is of course extinct now, but BJTs and MOSFETs. So now I'll assume that f of v is an odd function. Assume f of v is purely an odd function. If f of v is purely an odd function, if I look at the differential amplifier, it doesn't have any even component at all, then I1 plus I2 will not contain any even component. It will always have a constant value which is equal to I0. So there won't be any harmonic content from the supply. So if I choose a device which has a purely nonlinear, odd type nonlinearity, so which means it has only powers of odd powers of the voltage, the current is dependent on odd powers of the input voltage. In that case, if I use such a device, then from the supply you will always be drawing out a constant current. There will be no even harmonics present in the circuit, and in fact individually the devices in the differential pair will be carrying odd harmonic currents. In fact, there will be no even harmonics present in the circuit. Similarly, if I choose an even harmonic device, so meaning the device characteristic looks something, it has one term which is proportional to the input, the remaining terms are only even powers of V. In that case, the current drawn from the supply will contain all the even harmonics, and the differential amplifier, interestingly, if you see, because all the even terms fully cancel out in a differential amplifier, you will only be left with the first term. So if you can in theory build a device which with one proportional term and all even order terms, then it will be in theory, if it obeys this equation, the differential amplifier will be perfectly linear. So if I assume a pure second order square law characteristic for a MOSFET and use voltage biasing, then even though it's a square law nonlinearity, I will see a perfectly linear amplification without any harmonics in the differential output. So that's it about our discussion on voltage biased amplifiers, voltage biased differential amplifiers. What we have seen here is that the voltage biased differential amplifiers contain harmonics that is dictated by the device characteristics, which is f of v. And if I split the device characteristics f of v as an odd function and an even function, we just showed that the differential devices, the differential currents in the devices contain only odd harmonics, and the common mode current, which is the current drawn from the supply, it contains only even harmonics, and the individual currents I1 and I2, the device currents, contain both even and odd harmonics. So that's the conclusion that we have drawn out of a differential amplifier with voltage biasing. Now in a similar way, we will try to intuitively see what happens when you have a current biased differential amplifiers. Now in case of a current biased differential amplifier, one condition, even in the presence of input voltages, when you apply an input voltage, a differential input, this condition always has to be satisfied, which is the sum of the two currents in the two devices, I1 plus I2, is exactly equal to I. That condition has to be satisfied. So this condition has a very interesting consequence. Now let's assume you have applied a positive voltage at this device and negative voltage at the other end, and for the time being I'll assume the devices are also identical to each other. Now since the gate voltage here is positive, we are going to assume that the current I1 is going to increase by delta I1. And since this voltage here is negative, we are going to assume that the current through this device is going to reduce, rather I by 2 minus delta I by 2. But even if it is increasing or decreasing, we always have to satisfy this condition, I1 plus I2 is equal to I. Now if I substitute that, I'll end up with a condition delta I1. In this case, if I assume I2 minus delta I by 2, then delta I2 should be equal to delta I1. Meaning, if this current increases by delta I, the current in this arm, the other device, has to decrease by the same amount. And that condition is imposed by, and that result is actually imposed by this condition. The sum of the two currents should always be constant. So which means if I try to draw the loop of current which is flowing through this, the current will flow in this way. So that because this current here is incremental change here has to be 0 because it's a constant current. Any change here will be fully absorbed by this device itself. Now we just saw in the previous example, the odd harmonic currents tend to flow this way. So which means by construction, this device, this amplifier, differential amplifier, cannot have even harmonics. Because if there is an even harmonic current, then both those currents, both the even harmonic currents will be flowing in the same direction. Previously, both those currents were directly flowing into the ground because it was a voltage source, and the voltage source can take any amount of current and maintain the voltage there. But now since it's a current source, there is no path for the second harmonic currents to flow. So therefore, the second harmonic currents will cease to exist in this circuit. There will only be odd harmonic currents present in the circuit. So then how is it possible? It's possible because here we have connected a current source. The source voltage here has a freedom to change. So the source voltage will change in a nonlinear way, in such a way so that the currents flowing through these two devices will only contain nonlinear terms. So we'll revisit that point, but first I'll assume that if I assume the input current I1 is some function of Vi, so here I'm assuming G here, so I've started with a device I given by f of V. But now I'm just writing this current I1 in terms of Vi with a function G. So some other function G, and similarly I2 is given by I by 2 plus G of minus Vi by 2. Now here, using this condition delta I1 should be equal to minus of delta I by 2. If I write a plus sign here, from that I can directly say that G of Vi by 2 should be equal to minus of G of minus Vi by 2, which means G of x is an odd function. So if your I2 increases by a certain value, then I1 increases by a certain value, then I2 has to decrease by the same amount. So therefore, even whatever be the characteristic of f of v, g of v will always be odd. In fact, you can do a large signal analysis and derive an expression for I1 and I2. Most of the standard textbooks contain these results. I've written only the general expressions for these results. If you take a bipolar junction transistor with an exponential characteristic, you can easily show the individual branch currents I1 and I2 will be tan hyperbolic. It will have a tan hyperbolic dependence on the input voltage. And for a MOSFET, again the characteristic will look something like this. The input voltage Vi, it's Vi here, Vi into root of A minus B into Vi whole square. A and B here are constants, so that will depend upon the device dimensions and all that. Again, you can very clearly see that both these functions are odd functions. So that's one very interesting fact about MOS amplifier, differential amplifiers with current biasing. When you do differential amplifiers with current biasing, because no current can flow through this, no signal component of current can flow through I0, the circuit will attain an operating point where it will only produce odd harmonics, and that odd harmonics will flow in a loop as shown in this figure. So as far as the supply is concerned, it's always going to draw a constant current because the current that's going into the ground is constant, so the current drawn from the supply will also be constant. So supply is not going to supply any harmonic current. It's going to be a constant DC current I0. So this is how the current is going to flow. This is how the harmonics are generated in a current biased differential amplifier. So even if I take f of v to be a square law device, so which has only even harmonics, even if you assume a square law device, this circuit, a current biased amplifier, will have no even harmonics. Both the individual currents I1 and I2 will contain only odd harmonics, and the difference I1 minus I2 will also contain only odd harmonics. The circuit itself obliterates any even harmonic component that's present in the circuit. And how does it do that? So we just intuitively said that the source voltage here can move. The source voltage here can actually change. The source voltage will change in a nonlinear way so that the currents flowing in these two devices will only be odd harmonics of the input frequency. Now what happens if I have mismatch? If I have mismatch between the two devices, again using this condition that the sum of the two currents always has to be constant, so even if there is a mismatch, I can always assume there is a delta I1 change, and instead of I0 by 2 the current is I1 here, the DC current, and in the second device current is I2, and I'm going to assume delta I by 2 is the increment in the second device. We will end up with the same condition. So even if there is mismatch in the circuit, the increment in this current I1 will be exactly equal to the decrease in the current I2. So irrespective of whatever be the nonlinear characteristic, even in the presence of mismatch G of V, the currents will always be having odd harmonics, will only contain odd order terms. Okay, it will odd order terms or odd harmonics of the input voltage. And this is forced because of the constant current source. Now if the current source has a finite output resistance, then in that case you will have even harmonics as well. So just to illustrate how does that make sense, I mean, even if I have mismatch, again this is something most of you must have at least solved in basic analog courses. Now let's say I have an amplifier, a differential amplifier. I have sized one device twice compared to the other device. So at DC, this device is carrying 2I by 3 and this is carrying I by 3 amount of current. The current is half compared to this device, W bar is also half. So therefore if this device has a GM of GM, this device is going to have twice the transconductance, which is 2 GM. But then we have to, I'm just considering only the linear component and trying to show that how is that the magnitude of both the currents become equal. So because this current here, the sum of the two currents is supposed to be 0, you get this condition GM1 VGS1 should be exactly equal to GM2 VGS2. And that will be possible if your input, say in a purely differential circuit, your input will split equally between the two devices. If the first device small signal voltage is Vi by 2, the other device it will be minus Vi by 2. But now to meet this condition, since your GM1 is more, the VGS of that device will be smaller. So the voltage will distribute itself asymmetrically. So by doing so, these two currents will become equal. The increase in I1 will become equal to the decrease in I2. That condition is met. So a similar way we can analyze and think about it for odd harmonics as well. Every power of 3, 5 and so on, we can think your voltage will distribute in such a way so that the currents, that an increase in this current should be equal to decrease in this current. So this is how an amplifier or a differential amplifier with constant current biasing will ensure that there is only odd harmonics present in the circuit. So if you recall quickly, for a differential amplifier with voltage biasing, the harmonics present in the circuit or the individual currents I1 and I2, they contain all the harmonics that the device nonlinear equation permits. But here in a current biased circuit, I1 and I2, irrespective of what is the characteristic, f of v can be even, f of v can be odd and even, f of v can be purely odd, I1 and I2 will always be odd, will always only contain odd powers of the input. So that's it about the comparison between a constant current biasing and a constant voltage biasing. And just to quickly end the discussion, when you compare it with a current biased single-ended version of a current biased amplifier, again here it will contain all the harmonics that the input permits, because you don't get that benefit. You get this benefit only in a differential amplifier. You don't get that benefit in a single-ended amplifier. Thank you.